Welcome again. I will not say much more because this will become repetitious very soon. First question, first and foremost, who has any idea about iOS development whatsoever already? All right. Who has some apps in the store? One. Okay. So for the rest, I will assume that you're mostly Java guys and just want to look a bit beyond what's in this strange Apple world. A few words about myself. My name is Daniel Schneller, and I'm the primary development lead maybe for this center device product Mirko talked about this morning in the keynote. And my main development focus is on the iOS app, but I also manage in a way the Android guys that are sitting here in Novi Sad and working for Codecentric and center device in turn. So if there are any questions about that, ask me about that later maybe. Agenda, just rough overview of what this is going to be. Probably the time will not be enough. I will try to show you how to come up with a complete, simple picture viewer application over the course of these remaining 39 minutes maybe. It might be a bit hasty in the middle, but I will try to answer any questions at the end or outside during a cup of coffee or something. So first of all, of course, a bit of history, iOS, what is that anyway? Then a few words about the tooling. I assume most of you will be using IntelliJ or Eclipse or something for Java development. There are a few differences there. Then a few introductory steps, maybe a bit mapping Java constructs to Objective-C constructs, which is the primary language used for Mac and iOS development. Then a few more advanced things that might be surprising or especially strange to someone who's mostly proficient with Java or languages on the JVM in general. Then the coding demo, and I'll see how quick I need to be to get through this. At the end, we will have the application. It is ready, so no worries there. And then some recap and questions. So what's this iOS thing anyway? First of all, it wasn't always called iOS. It was called iPhone OS first. When the original iPhone came out in 2007 and there was rebranded iOS, I think they first needed to get some legal stuff worked out with Cisco, who still owned the trademark, or at least at the time owned the trademark for iOS. But they really wanted this, and I assume that quite a bit of money changed hands. It's a Unix-like system. It's a BSD system, same as macOS 10. So that's where there is a strong resemblance. When you know Mac programming, you feel not right at home with iOS development, but many of the frameworks and especially the lower levels of the OS are very similar. It's a fully preemptive multitasking system. That is something that especially, and right from the start. So people complained at the beginning that iOS, there was no multitasking and it was somehow limited and not a real operating system. But under the covers, this is like OS 10. This is Unix. There is lots of processes, but they decided not to let multiple user applications run at the same time or in the background. So there is a difference there. And yeah, as of this year, very recently, they introduced the iPhone 5S, which is the first one with a 64-bit architecture, so it's even a bit closer now again to OS 10. But this is just the history. It's not only running on the iPhone, it's also used to run the iPad, which is probably mostly known, and the iPod Touch, the phone's little brother, and also the Apple TV. That's basically just a phone without a screen and in a nice little box with an HDMI port. The development you need to do on OS 10, so if anyone was hoping, at least with Apple's tools and the official way, there is no way to do this on Windows or Linux. I just recently read that there is some commercial Delphi, the most recent Delphi version allows you to buy a plugin or something where you can do Objective-C and, oh no, it's not Objective-C. I think they use Delphi as the language, but you can compile for iOS. I have no idea how well that works. But the official way, of course, is only Apple hardware. It's an ARM CPU, so if you're really deep into assembly stuff, that is different from Intel assembly that you might know from PCs. And the tool chain is actually cross-compiling on the Mac on actual Intel processors down to ARM code, and that is then transferred to the device. And there is a stripped down version. It's limited in several ways of iOS, even for x86, and that is this iOS simulator that is run on the Mac, where you can try out your applications without having to install them on a device every time. This speeds up the development cycle. And this is actually the same operating system, but compiled for a different processor architecture, and it's simplified in some ways. So tooling first, because everyone loves great tools. There is Xcode, and the small byline there is the poor man's Eclipse, or IntelliJ, if you like that more. They've come a long way over the past 2-3 years and made great advancements, but it's still, in my opinion, not up to par with any of the popular Java development environments. The editor is worse, and debugging is strange sometimes. So anyone coming from Java and then trying this for the first time, at first sight it looks great. There is like pop-ups for code completion, and there is a refactor menu. But when you try to use these and expect a few things to happen that you just take for granted when you know Eclipse, you're in for a surprise, to say the least. Version control, this is even worse. I haven't tried the latest Xcode 5 has apparently improved this again, but so for version control needs, use a separate tool. And it of course does build and deployment, so including deploying stuff to the store when you're finished and want to upload this to the App Store. This is all now integrated into Xcode. At the beginning there were separate tools, but it takes care of signing and managing the accounts for the App Store and uploading the stuff and verifying and whatnot. So that's actually pretty nice. This is what it looks like, mostly. This is Xcode 4. As I said, the most recent one just presented this summer is Xcode 5. It has a bit smaller toolbars and a few less gradients, maybe, but this is still the general structure. So to go through this, on the left-hand side, some kind of a navigator that you might also know from most other tools. This one is a logical view. This is not a file system hierarchy necessarily. It can be, but it's a project file, great for merging. Some mixture of JSON and XML that is describing this layout there, and if two people make changes to this, happy merging. But also this has gotten better. Then this is what they call the assistant editor. Up there is a mode switch, and this is now set to assistant editor. So on the left-hand side, this is split again in two, but this whole area, they can visually design user interfaces. And then wire these, for example, this background here, by drag and drop, you can wire this up to the source code and say, okay, in source code, this property, which is called image view, is representing this piece of image view on the screen. So you can do visual layout stuff and then hook that up to the code without actually typing anything. If I drag a line, and there is this one actually is generated. So if I, for example, took this label and drew a line up here, it would insert another line, and I could give it a name and stuff like that. So that's the basic idea. You need not do it like this. You can do everything in code if you prefer that. There are people who hate this interface builder thing with a passion, and they'll do everything in code. I think it has its advantages, but if you do more complicated stuff with deeper view hierarchies and stuff, that might become not so nice visually, but and you can do any mixture of the two. Next is the simulator that I talked about. So when you click that big run button in the top toolbar in Xcode, it will fire up the simulator. There you can pick which iOS version you like to test against, and it will bring up either a phone or a tablet one. You can change if you have Retina display or not, and several other aspects of it. But then it will run your application in this Intel version of iOS on your computer. Problem there is, it's a simulator, it's not an emulator. With Android, it's emulating a complete device, including all the hardware and limitations of memory and disk space and whatnot. Whereas in this case, this has full access to your Mac's resources. So if you use an API to query how much RAM is available, this small iPhone might tell me 16 gigabytes. No problem, just load everything into RAM, keep it coming. And then you install it on the device, and this one has at most 1 gigabyte. That's something you should know. But it's good for very fast iterations, and for like just the behavior of the app, this is okay. But for everything that has to do with performance or storage or network traffic, you should really test on the device, especially if you plan to release something to the store. Then there is instruments. That's the profiling and performance debugging tool that comes with the development suite. By the way, this is all free. You can just download Xcode from the App Store, and it will install and bring all those tools with it. It works with the simulator and the device. Some tools do not work in the simulator. For example, analyzing 3D performance doesn't make much sense if it's running on your local graphics, which is completely different from the phone maybe. But this, for example, is like a timing trace. Here you see the CPU time that is being used by system or by your own call, depending on the color, and the frames per second. This is especially great if you like scroll through a table and it's jittery and stuttering, and you want to know what's going on. You always, everything you read from Apple, they always say, keep it at 60 frames per second. It should be absolutely smooth scrolling, no matter how complicated the stuff is that you're doing. Then you need to refactor your code, make it asynchronous or whatever, but keep it smooth. Of course, that's easier said than done. But this is what you should strive for. And here you can see, here the frame rate was pretty good, even though there was computation going on. So actually, that's the tool you need. All right, enough for the tooling then. You will see more of this in the coding demo later. Some first steps with Objective-C. It's a C-based language, and it actually is C, so you can write plain C code, and this will be compiled, no problem, just like C++, for example. The first difference you might see is that the files do not end in .c, but in .m for module or something. I have no idea. But it's like a set of object-oriented additions. It was influenced by Smalltalk on top of C. It's a dynamic language. You can, of course, use classes, and the compiler will do type checking and stuff if you tell it to, and if you let it, by writing explicit classes, but at runtime, it's all dynamic. So, source of great bugs, I can tell you. There is a runtime that's providing these object semantics. The compiler will go and compile everything that you write as object method calls and stuff like that down to C function calls. So that's when you look at the output of what the compiler does, it does not necessarily resemble much of what your source code looked like in terms of structuring because of this. And to keep this illusion running, there is this runtime which gives you base classes like NSObject. It's in a way comparable to the Java runtime environment. It's being mostly, if not only, used by Apple. I haven't heard of any really famous projects that use Objective-C as their primary language, but they are evolving it because they want to push people to develop for the iPhone, especially for iOS. For the Mac, that's like a byproduct. It's also nice, but there's been great strides forward in the language over the past couple of years. And most importantly, even though it's the last bullet point here, it has a really strange syntax if you know other languages. A few of the key differences, and then we'll have source code examples. Memory management is at least not fully automatic. There is no garbage collection. There is a system of reference counting. They simplified that, I think, last year with something they call ARC, stands for Automated Reference Counting, which helps you a great deal. Most of the memory management code that you wrote before, you could just remove. There are a few edge cases where you need to know about this system so that you don't introduce subtle bugs, but it's gotten way easier. It almost looks like it's garbage collected. They deprecated the garbage collector. They used to have one for OS 10 at least. They used it, I think, only for one of the earlier versions of Xcode, which was dog slow. And then after, I think, just 2 years, they deprecated it. They said, this is going away. We will not support any garbage collected applications, even on OS 10, I think as soon as next year even. And for iOS, it was never a topic. There is real pointers, which means you can fuck up real good. There is no namespacing, from the .NET side, or packages. Everything is in one flat namespace, means that all your classes should use some 3-letter prefix, and then you hope that no one else is using the same prefix and you want to use code from them, because then you're in for fun. In practice, all of the Apple stuff is either prefixed NS, which still stands for next step, which is the base of OS X, and UI for all the iOS-specific stuff. They reserve the right to use any two-letter prefix for their own purposes. So, for example, there is MapKit, which gives you Google Maps and location stuff. They prefix this with MK and so on. So it's actually a pretty good idea to use three-letter prefixes to prevent clashing with some naming that might come in future iOS versions. There are modern features as well. So they have closures already. They call them blocks. They have collection literals, coming to a Java version near you real soon, TM in 15 years maybe. And they have real properties similar to what C#, for example, has. Exceptions are present. They are hardly used for anything but to really crash and terminate your application. So that's a key difference to Java, where they are like everywhere and used for anything from small validation error messages to crash my application. So let's see a few examples of what Java and Objective-C code looks like. This is simple. This is still simple. I mean, it's called bool instead of boolean, and it's yes and no instead of true and false. There are actually some macros so that you could use true and false. You could also write 0 or anything other than 0, which is the C showing through already. This is also still simple. These are all the simple examples, just to get us going. Whereas in Java, everything inherits from object. Usually, all the Objective-C stuff inherits from NS object. But you seldomly find references. Usually you see this ID. And ID means this is an object. I have no idea what it is. You can send any kind of message to it. Basically, it switches off this compile time checking of, is this a method that the target should know? So if you're writing rather dynamic code, you use IDs, and then it will say, okay, whatever you do, you must make sure that this works at runtime. I'm out of here. This is what a dictionary looks like. A Java hash map or a map, where you say object dot method name, and then the two parameters just by the order, it's key and value. In Objective-C, you can define a dictionary, which is their term for a map, and you can access the key like this. You just open these brackets, put the string key, and the value is assigned to it. Ignore these @ signs. These @ signs, you will see them all throughout the code. This is just to prevent naming conflicts with C itself. So this is a string literal. The compiler will turn this into new NS string with this C value key. You can ignore this. Classes are defined like this. Someone might find this resembling Haskell maybe, who still knows that. You have an interface which includes all the methods that can be called publicly by users of your class. And then there is an implementation, could be in the same file, but it's 2 sections, which can have any amount of methods that you need to implement this privately. And the inheritance is done with a colon instead of this keyword extends. But apart from that, it's the same. Here again, these ats, just to prevent that someone using C code in his Objective-C program that might use the word interface for something else or any of the other things that might clash. So they prefix it with an at sign. This is a source of confusion. What's an interface in Java is not this interface in Objective-C. This is just to keep this public and private parts separate. But this does not mean I implement this interface in the sense of I must provide a method called ABC with this and these parameters. Instead, that's called a protocol in Objective-C. So this is one of these things that you can trip over when you're just starting because the terms are like overloaded with different meanings. And this is what it looks like when you implement an interface or a protocol. You put this into angle brackets. The implementation doesn't say anything about it. And abstract classes do not exist. It's just by convention. What I usually do is I implement the method stub in what I deem is the abstract base class and let it throw a not implemented exception or something that immediately kills the app so that you at least find it. But there is no compile time checking for this. Excuse me. Packages, as I said, just a 3-letter prefix. I used CDS for coding Serbia, but this is it. Method definitions, Java side, just void, name, no parameters. Here you say a minus, next line will show you why. Return type in braces, and the name of the method again. No parameters means nothing comes behind it. What's static in Java is a plus. So this is an instance method, and this is what they call a class method, which can be called on the class itself without needing an instance. String, already said. The class name is NSString, and there is a pointer. Usually just sprinkle a good amount of these stars in there, wherever you would just have a regular Java class used like this, and you'll be fine. And the @ again. Calling a method, Java side, object dot method call, and this is where it gets strange. When most people look at a good chunk of Objective-C code, they see all these angle brackets. And what's that doing there? Well, because there is no dot here, they somehow need to make sure that S is what gets this method call. So what do you do when you have nothing that connects it? Well, you put it in brackets. Looks nice if you chain these. Can become pretty ugly, and you can also imagine that this is not easy for code completion. When you try to type it like this, it puts opening brackets wherever it thinks they might need to be. Oftentimes, this is not where they need to be. So NDC parameters are, here there is nothing there. Here you put in an int, and here a Boolean maybe inside these parentheses. Nothing, and here they are separated with a colon. So that's the equivalent call. Just the idea is that this is creating a new class or a new instance. That's you send the class an alloc, call alloc, and then on that what alloc returns, this pair of brackets gets sent the init, and this one then returns an actual instance of my class. So it looks strange, but it's actually pretty useful because you can do things like this. Whereas here on the Java side, you need to know what these two string parameters are and in which order they are used. And what the 7 means, I have no idea unless I look up the documentation. Objective-C is much more verbose. Lots of explicitly written stuff, and the method name actually for this one is whoops, let me get back. The method name is everything that is green. So actually the method is called init with last name, colon, first name, colon, played in movies, colon. Including the colons, that's important. That is not named parameters, so you cannot just exchange these. The ordering is fixed, but you then sprinkle the actual parameter values in between. So this is just, would be one line if there was enough space. But it makes it much clearer what is going on. So you say, init a captain object with the last name Kirk and the first name Jim, and the value for played in movies should be 7. And they are cleaning up upstairs. So this is, this is where code completion becomes really helpful, but it also has its advantages. Some more advanced stuff, maybe. The Objective-C bag of tricks. First of all, there are no null pointer exceptions. You call something on an object that is not there, that is nil. So what? Nothing will happen. If it expects a return value, you will get nil again. No exceptions, and you can very nicely chain calls through that and be safe that not one of them in the middle will return a null and then blow up your application. And this is a pattern that is used everywhere. So this is not something like, okay, you can do it, but you really shouldn't. Everyone is using this, all the frameworks, all the class libraries. So what looks in Java like this, give me the first lowercase string from a list of strings, lots of null checking. How many lines are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something like 12, 14 lines. Looks like this. You get the parameter, you call first object, description, which is toString, lowercase string, that's it. If anything in the middle returns nil, you just get nil back. And this is exactly what the Java code would have done too, just with lots more checking. So it's less prone to crash. Of course, it can make for subtle bugs. Something doesn't show up on the screen and you think, what's going on? Well, one of these might have returned nil and you didn't expect that, but it still did. Good luck finding that. So it has its pros and cons. Protocols, remember that's Java interfaces, can have optional methods, which is actually really great. No need to define sub-interfaces and another one and another one. You just say, okay, this is a set of required methods and everything else is optional. And the users, when you have a delegate object, for example, that's what it's usually used for, say, these two must be implemented because I really need those values to execute the program. But the rest is like convenient stuff that you might want to implement in your app or not. You can check at runtime, will this one respond to this method? If not, then you do not do the call or do something else. And if you see it's there, then you can call it. It's pretty nice. Looks like this. Everything that would be above this line would be the required. You could write at required if you really wanted, but whereas these two, you can implement them if you say my class implements this UI table view data source protocol, but if not, then you just leave them out. Categories is a great one. You can extend classes with new functionality at runtime, even those classes that are not your own, so like framework classes. That is a great tool for decoupling and lots of other things, but let's look at an example. That's, for example, there is a class NSNumber, which is basically Java-like number. And it does not have a method human readable file size, something that you might want to have in a file manager where it says 7.4 gigabytes, but if it's only a few hundred bytes, you would want to see it like this. There is something like a Java simple data or simple number formatter stuff, which is called an NS byte count formatter, which actually does this. But wouldn't it be great if this number object just had a new method, give me the human readable file size without me having to pass it into some kind of formatter object, which I need to create or store somewhere that could be thread safe, might not be. So I just write this. There is a corresponding interface, but on the slide now, just the implementation. On this NSNumber class, which exists in the system frameworks, I create a category in this is the syntax, and the name of the category is CDS, my prefix, human readable. And when I do this, and in my application, I import this category's header file, all my NSNumber object all of a sudden have this method. And when I call this method at runtime, it will go to my implementation and execute this. So actually, the self, Java's this, the self that is being used here, this is from NSNumber. So it's really like a method that I just bolt onto it and it just works. I can also replace existing methods, but that's a difficult thing. Another one would be like this. I have a dictionary, like a hash map. And it would be really nice if I want to write something that is doing web communications. Then I do a string with URL encoded entries. I just add this, implement this once, and then all my dictionaries where I need it can do this automatically without calling anyone else. Really nice. This is an ugly one. Method swizzling. Usually done in conjunction with these categories. You can replace implementations of classes at runtime and call to the original implementation. So this is like every Java programmer, I make this private. Complete horror movie, because someone goes in, grabs your implementation, puts in another one, and maybe calls to this one, maybe does not. But it allows for very nice things. For example, when you do not have access to Apple's source code. So unlike Java, where you have the source for the query, you do not get this. You just see what it does. And for debugging, you might want to like add some debug logging output. Whenever one of these internal methods is called, you can do that. So for example, I want to have all my views that make up my UI have a border. Usually that is not possible. I write a small category. Two most important lines of this category are these. I just get the right implementation here, and this is my new implementation, swizzled in it with frame. The constructor of a UI view. And I say, okay, I want a border width of 2 and a red color for this border, and then I just return this. And using this code, I exchange the implementations. I say, okay, the original implementation of the method you can get from this Objective-C runtime calling this function. Give me on myself, on a UI view, this selector, or the method init with frame. Mine is this one, and then exchange implementations. That's pretty nifty, because this is what the demo app will look like. And if there was some bug with the UI layout, I could just swizzle a bit and get this. And see, all right, maybe this image view has the wrong size. It should extend all the way to the edge of the screen, maybe not. So this is done by adding code to the private constructor of this internal UI view class. Pretty nice. Usually powerful, but yeah, enables advanced bugs. That's for sure. All right, so much for the theory. Let's now switch to some actual code. This is the simulator. So when I start Xcode, I click Create New Project, and then yeah, this is going to be fun. I give it a name. Here it asks for the class prefix, and in the end, I click next a few times and get a new project. I have prepared something which I will use now, just because of the time. So let me switch to this. Open the existing project. Oh, crap. Barely fits. So it doesn't fit at all, actually. Okay, so can I resize this even smaller? I would have hoped that it would have at least 1024, but this is 800 by 600. I think there has been no Mac for 10 years with this resolution. Still too wide, my goodness. So this is the editor. You see here, this is just the default application template that I use to create this project, and I can fire this up in the simulator. It's just a table view. I can add some things. In this case, it will just add a new date object whenever I click this plus. And when I click on one, it shows me a detailed screen, which just shows the label full screen. That's the basic application template. Everything usually is model view controller based, so that's the paradigm that spans everything, all applications, and you're really suggested to follow this, because otherwise you're working against the frameworks. This is the code. There is the storyboard file, which has the UI. Let's try and get this small enough that you can actually see something. So there is the table view. There it is. And here you can see the outline of how this UI is constructed. Okay, this doesn't make much sense. You will not be able to see anything. That's shit. Let me move forward a few steps so that we actually get somewhere. See something useful. I will skip a few of these first steps, because otherwise time will be too short and you cannot see much of it anyway. I invite anyone who wants to see this in more detail to visit me later outside, and I will be happy to show you on a screen that actually has a bit of resolution. All right, so this is already changed now, so if I run this again, stop the existing one. The simulator has a scale down to 50% mode. That's really helpful here, but where is it? There it is. So what this application does is, it's like a Flickr viewer maybe, just because I didn't know what the network would be like. These images are local and they are loaded from the disk with a
random delay of between 1 and 2 seconds or something. And then they are added to this table, and you can scroll through here. There is one of these. You can rotate. I think this one should already have pinch to zoom, and then move around. This is all basic framework functionality. This whole app I did in something around 8 hours. Just because I want to leave some time for questions, let's move forward all the way to step 9. Kill this. I'm going to show you some source code too, just for good measure, so that you believe me that it's not just all painting. Get this. You believe me? That's nice. So you can believe me that there have been a few more classes added. For example, this is now this this category thing that I had on the slide too. There is one on UI image, which is the class that can load images from the file system and display it. It can be displayed then. Here I added a generate thumbnail method. So as soon as I import this, any image I have in my application now can scale down to a thumbnail of this size. There is the model class for this model view controller thing. See, the syntax is a bit hard to get used to, but after maybe 2 days it makes click, and then you can read this just like Java code. Then you just, it's fine then. It does things like read some EXIF information, so you can use framework functionality to get the height and I don't know, the date when this picture was taken. So if I run the application again, you will see that now the table has some more details, which are actually read from the JPEG file. It always needs. Oh, I added a splash screen. Yeah, also nice, and some placeholders while it's loading. File size, the exposure time, and now this one doesn't include a date for some reason. The resolution. Let me rotate this so you can better see. So yeah, there is actually even a few images taken here in Serbia. I think. I thought. Did you see one? That's a nice perspective here. You cannot really see. See, next step should be a search feature. Probably at the very bottom. Serbian honeybee. So this is in the park right outside this building. So, and now it has a. Thank you. You can click and it will hide this. You see that the view actually extends behind this bar, and just by showing and hiding it, the system will make sure that this transparency effect is in place. So you get a lot of stuff for free. For something as simple as this, display a table, display a picture, maybe load something from the network, this can be all done in 1 day pretty easily. And then you can start worrying about making it nice and look good and give it some color. You see that's with routine comes that. And the last demo I would like to show you is this, this method swizzling thing, where it actually replaces stuff at runtime. Go back to the file listing down here. There I have this category defined. This is the same code that was on the slide with the border. And you see now, if I make sure that this method actually doesn't do anything by immediately returning, the app should look like exactly the same. And when I go and remove this so that this this exchange implementations actually gets executed and exchanges something. Yeah, stop this one. You will see now that all the borders, including those that I do not draw myself, so this battery symbol, for example, this is handled by the system. But during my application, during the life of my application, it will execute my exchanged code even for these system classes. So it's pretty nifty, just for my application. So that you can see that whenever you run an iPad app or iPhone app, it process is responsible for painting that status bar. Otherwise, you could inject code into other apps, which would be interesting, but probably bad. All right, yeah, so much for the... I planned on much more code, but with this resolution, and because the slides took longer than I expected, okay, as I said. And tonight is the coding party, so I will bring this and we can make it a real coding and hacking party, if you like. So any questions that you might want to put up now that the demo, small as it was, is over? Thank you.